There we go. Yeah, we firmed up Miller Puckett and Damon Holtzborn will be presenting on November the 18th. Lara Lewinson will be presenting her work, she's made some amazing strides recently. She'll be talking to us later this month on October 28th. And this session and next session, Onur's going to be telling us about machine learning, which I'm particularly interested in because I don't know much about it myself. So I think I'll turn it over to Onur. It's like, what, 1 a.m. your time over there, I think?
1:15, yeah.
1:15, okay. So here we go, take it away. And we may not go the full time tonight. This is pretty dense stuff.
Yeah.
Yeah, go ahead, take it over.
Yeah, I mean, what I thought was today, like, yeah, probably today will be shorter side. Hopefully, I don't know what will happen. Depends on you guys also a little bit. So I'm planning to mostly focus on some general concepts of machine learning rather than like specific audio applications today. And also like at the end, not at the end maybe, but like at some point, we will also be building a very simple neural network. First, I'll do it in Python, and then we're gonna translate that code to RTC mix. And we'll see how that goes. And then next week, my plan is to cover like more practical, like hands-on applications and tools maybe. Also a quick disclaimer, like I'm not a machine learning expert by any stretch. So what I do is that I try to use machine learning in my music in a rather limited way maybe. And maybe those of you who are in STEM fields may know more about it or like use it much more than I do. So feel free to jump in and like correct me if I say something that doesn't sound quite accurate. And also, like this is a very, very complicated topic. It's not like 2 weeks are just not enough to cover like this thing in any kind of, and you know, I mean, maybe I can basically like show you like little bits and pieces of things, and the rest is up to you. So if you get confused, like please don't wait until the end to ask a question. Just interrupt me anytime, and but we'll also have probably like time at the end, you know, for questions. So, all right. So, what is machine learning, and how does it relate to like other buzzwords like artificial intelligence, like neural networks, deep learning? I mean, you name it. I'm sure like most of you like at least heard about these terms a little bit before. So I'd say a very broad definition of machine learning would be that it refers to computer algorithms that learn and improve from experience without being explicitly programmed like traditional algorithms. Maybe that sounds vague a little bit, but the difference with traditional algorithms is that, the difference between machine learning and traditional algorithms is that we don't directly teach a machine learning model, let's say, features of the thing we're training it to recognize or predict. That means, for instance, we don't have to teach the model ways to recognize individual features of a face for it to perform face recognition, for instance. Or, I don't know, I mean, it's, again, like for, let's say, translation, machine translation, the model doesn't have to learn, doesn't have to know much about the language. We don't have to like teach it like phonemes or anything like that. It can do this thing automatically in the training phase. Whereas in a traditional algorithm, like we would have to maybe code something in there, some kind of if then else statements or something for it to kind of stop, you know, do something like this. Usually these machine learning models achieve this like whatever recognition or prediction after being fed a large amount, well, it doesn't have to be large actually, a large or small amount of relevant data. And then it kind of learns by itself. So we can say that actually machine learning algorithms are usually much more opaque than traditional algorithms. But that said, and this is an important thing, this is not like some kind of black magic, you know, because I've heard from people that, you know, like we don't know exactly what's going on in the machine. It's partly true, I would say. And we'll get to that a little later. But basically, in its essence, ML is based on, I would say, like statistics and like pattern recognition, which usually leads to kind of like some kind of prediction at the end. I guess, yeah, the buzzwords again. So how does machine learning relate to artificial intelligence or neural networks or deep learning? So I would say that, and I mean, it's not just me, but like it's a general consensus is that machine learning is a branch of artificial intelligence. There are some people, especially after 2000s, because like machine learning kind of went its own way because of like certain advancements in hardware. So they kind of consider it like separate from artificial intelligence, but the general consensus that it's a branch of artificial intelligence. And then neural networks, for instance, are, they can be considered, okay, so they're not, I wouldn't call them a branch within machine learning, but they're a tool or that is used, you know, within machine learning. And neural networks are used for different methods of machine learning. It's not just one method, but I guess these days the main kind of like the most famous one is deep learning, for instance. And we'll talk about that in a second also. All right, so what is a neural network? Or they also call them like artificial neural networks to distinguish them from biological neural networks, or they're also called like neural nets in short. All right, so these are computing systems vaguely inspired by biological neural networks. And I have to like stress the vaguely part. It's because there are some similarities, but actually like they kind of also differ from biological neurons, or these, I mean, I wouldn't call them biological neural networks, but like an artificial neuron differs from a biological neuron in certain key ways. And we'll talk about that as well. But I guess the similarity is that just like biological neurons, artificial neurons can also receive the output of another neuron as an input. And as far as I know, and correct me if I'm wrong, if maybe some of you can answer this thing, biological neurons usually have two states, not usually, they have two states, either on or off. So once the input to the biological neuron passes a certain threshold, the neuron fires. I mean, this behavior can also be basically imitated by artificial neurons using thresholds, but they don't have to exist in a binary state like a biological neuron. Their output can be manipulated using certain activation functions. Again, this will be explained later. But an activation function basically just modifies the input that comes up into an artificial neuron and just basically like it affects the output. And then we come to deep learning again. So deep learning is a machine learning method based on neural networks. It's not the only machine learning method that's based on neural networks, but it is these days the main one, let's say. And the deep part refers to having many hidden layers of artificial neurons and many weights attached to them. So what is the weight here, the term weight? I guess for now, just know that like in the context of machine learning, it basically refers to a coefficient of some sorts attached to the inputs of individual neurons. And they determine how much a certain input into this neuron or this algorithm, let's say, affects the final output of a neuron. And basically the breakthrough like in deep learning or deep neural networks came thanks to a couple of factors. One is a huge, large amount of data that we have right now, we have access to. And maybe equally important are GPUs, like GPUs really kind of like are progressing at, even though they're progressing like more in a faster pace than CPUs. And they're I believe in the late 90s or like early 2000s, it was basically kind of determined that GPUs are the perfect computing platforms for neural networks, especially for deep learning, when there's so much data to process. So I said earlier that this is not black magic, but a lot of people talk about also what we call a black box. And this is somehow related to the opaque nature of neural networks that I talked about. So when we talk about a black box in the kind of context of machine learning, or maybe like deep learning specifically, it may refer to two things. One, deep learning algorithm. So deep neural networks are, by definition, quite complex. They have like layers upon layers of interconnected variables that become, let's say, tuned as the network is trained on certain examples, data. And
let me
kind of like,
yeah,
sure.
I'm gonna interrupt here for a second just to make sure everybody appreciates when he's talking about neurons, he's basically talking about code constructions that you're going to see. He's going to show them to you later. And it's funny because the actual programming is pretty straightforward. But as Onur was saying, you can create these massive interconnected things where one part of code connects to another part of the code, connects to another. And that's where the complexity comes from.
Exactly. I mean, a single neuron, like I'll show it to you in a second in code. It's not very like difficult to actually understand what it does. I think the complexity comes when they exist in layers upon layers. And the fascinating part is, like I told you, it's fairly simple to understand a single neuron. But how the machines kind of distribute the weights and how they modify them in the training process is quite fascinating. That's kind of the more opaque part. But anyway, so the black box part refers to these, let's say, hidden layers between the input layer and the output layer. And many of them, there may be like thousands of them, you know, in a kind of like very complex deep neural net. And it becomes like virtually impossible to kind of like trace how there are millions and sometimes like billions of like parameters combined to make decisions. And then the AI engineer at some point may actually like lose access to these parameters. And although like this particular network, deep neural network, does what it's designed to do, nobody exactly knows at that point how it does it. And this is a problem for debugging. One is a debugging problem. So if something goes wrong, how do you correct it? It's very difficult usually in this state. But there's also another kind of meaning of black box that's used, and that doesn't refer to necessarily the kind of like the structure, or let's say the architecture per se, but rather how certain companies, for instance, are using these proprietary kind of like neural networks or machine learning algorithms that are closed source, and we don't know how decisions are made. You know, like. And they're not always benign, you know. For instance, okay, like there's Google search algorithm, or like whatever, Facebook's news feed, or like Amazon recommendations. So these are not like dangerous things. I mean, per se, they may be dangerous depending on circumstances. But you know, we don't know how these things work exactly. We don't know what type of data they collect. We don't know what kind of like connections they make. But also think about something like algorithms, deep, you know, neural nets that are used for determining credit scores, or who gets to be treated in a hospital, like insurance decisions. Like these are also complete black boxes. We don't exactly know how they operate. And this is not an architectural problem. This is more of a, I don't know, a privacy and ethical problem maybe, I don't know. But it's good to mention this thing. Okay, so there are like I told, different methods, and like machine learning is, let's say, a branch of artificial intelligence, and there are also methods within machine learning, and you don't have to use, let's say, a single method for your application. You can combine many things, you know. So for instance, in a computational linguistics application, let's say, your neural network first can recognize like a language that's being listened to by the algorithm, some kind of speech input, and maybe also transcribe it. Then you can also, then afterwards, after you determine what language is this, and then it's transcribed, then you can deploy a Markov chain of some sorts specific to that language that can perform some type of natural language processing. And Markov chains are also like used in I mean, they're not obsolete for every kind of you know, use, I would say. They're still used in natural language processing. They work for certain things better than others, better than neural networks. Depends on the usage. And also, there's something called ensemble learning, which again uses different, let's say, algorithms, sometimes like different types of neural nets, but in concert with each other. So let's say 3 different neural nets look at the same data. For instance, let's say we have a model that tries to recognize an image input as either as a cat or a dog, you know. So let's say 2 of the models, neural net models, say that it's a dog, and 1 model says it's a cat. So in this case, we take the majority vote and go with the dog. And this is very, very useful for applications that demand like high precision, such as like medical imaging or like military technology. Like you just don't want your missile to land on like some random place, you know, like, so like it's has to be confirmed properly.
Maybe I do though.
Okay, so and also lastly, there are more than one way there's more than one way of basically classifying machine learning methods. I mean, it could be like I told you, like deep learning is one kind of, let's say, branch, but we can also divide them into supervised, like semi-supervised, or like unsupervised, like kind of ways. So for instance, supervised learning is the one you would encounter the most when you're reading about machine learning or like studying it, because and like some kind of like examples of supervised or semi-supervised learning are like linear models, logistic regression, which also will be related to the neural network example that I'll show you. Neural networks mostly, something called random forest. I'm not going to get into these details, but like just know that there are methods that are considered like supervised or semi-supervised. The distinguishing feature of supervised learning is that it's the data used for training the neural network comes with labels. And this labeling procedure is usually done manually by people. It can also be done automatically or like, you know, by machines, but it's not it's very, very common that data is labeled by actual humans. And with labeled data, the machine learning model learns to form a function that connects the input data, which usually comes in a vector form, to the desired output. So after the training phase, the model's accuracy is tested using unlabeled data. I mean, for instance, like when you're training, again, let's go back to the like cat and dog example, for instance. The model, when it's training, like it trains with images labeled as dogs or cats, and it tests itself like that, and it corrects itself. And when the kind of like training phase is over, then you can test your model on unlabeled data and see how it performs. And there are certain kind of like things that lead to like better recognition, or like it's not necessarily like more training doesn't always equal like better recognition, better predictions. We'll talk about that later a little bit more. And there is then the unsupervised kind of, let's say, classification. In this case, we don't know the labels, but we have some data. An example of, basically these unsupervised methods use clustering. It's like, they're kind of like distinguishing feature. What that means is that So we're basically asking the model to find patterns in our unlabeled data. And then when you basically look at the patterns or clusters, the algorithm finds in your data to decide which observations belong to what group. And I mean, I'll give you an example, for instance. So let's say you're trying to understand whether a given credit card transaction is fraudulent or not. So you have a bunch of transaction data, which is composed of, let's say, two variables. One would be the transaction amount, and the other one would be transaction time. I mean, there may be other parameters in real life examples, but I'm just giving an example. So this model can group a certain time, basically certain times with certain amounts. So then it kind of forms a cluster of some sort, and I can show you what these graphs usually look like. Just give me a second. For instance, all right, so. Am I sharing the right? Okay, so. Do you see this right now?
Yeah, but
K means clustering.
hang on a second.
No, we see your desktop.
Yeah, we're seeing your desktop.
I'm sorry. Okay, just give me a sec. That's not what I want to share.
Onur has too many screens.
I have too many screens. I thought this would be helpful, but in the end, actually, it didn't help much. Anyway.
Can I ask a quick question when you have a moment?
Of course.
Yeah,
of course.
just
this is a great time, actually.
okay. Rewinding to ensemble learning.
Yeah.
You have a bunch of neural nets, and they take a vote amongst the results. My question is each of those nets built in the same way, but they diversify because the data leads them into different conclusions, or are they actually different kinds of nets with different kinds of structure?
They can be totally different types of nets.
Okay. Is it common?
They can put different method.
Okay.
What's that?
So is it expected that they would be very, I mean, so not just a different net, but a different principle of construction?
Well, I mean, that can also happen as well. I mean, you don't want them to look at, let's say, if you want them to look at similar parameters or the same parameters, chances are it's kind of almost like a redundancy of some sort. So I would say, I mean, again, I'm not very experienced with ensemble learning applications, but I'm assuming that they wouldn't be radically different. They would maybe look at data from slightly different perspectives or something, or maybe take in one more parameter. But in the end, I think you don't want them to kind of give you I don't know, very different results. But usually they are neural networks. You're not, when I'm talking about ensemble learning, I don't think that one would be a Markov chain or something. Usually they're let's say if there are three networks, if there are three kind of methods, all three are likely to be, I think, neural nets. Okay.
Yeah, the idea is that they're basically thinking in the same way, though curiously enough, they come to different conclusions. And that's fascinating to me.
Well, they don't, yeah, but if the architecture is everything in this case, so you don't, again, the principle can be the same, there may be layers and layers of neurons there, but they can be structured in different ways. They can have different weights. They can have different numbers of layers. The activation functions could be different. I mean, do you see what I'm saying? So many parameters you can change even within the same architecture. So they don't have to be exactly the same. I mean, they can all be neural nets, but it just doesn't say much actually. I mean, even neural net is an umbrella term right now, if you think about it.
Yeah, that's where some of the black magic comes in too.
Right,
There's
so,
not
I'll just share this in a second. I mean,
yeah, there's not a straightforward kind of knowledge of what particular net architecture is going to work in what particular circumstances. You know, some of them will have different feedback loops. Justin just sent an interesting link in the chat showing some of the different architectures that you can do. So David, your original connection, your original question, they probably would use two different architecturally different neural nets to attack the same problem.
Yeah,
You know,
I mean,
that would be
this
kind
actually,
of a thing to do.
yeah, this link is great, actually. It really kind of like talks about different types of, today I'm going to first show you a perceptron. It's the simplest form. And that's, if you open this link, you'll see it there. And I mean, there are like convolutional neural networks, generative adversarial networks, like so many of these things. And like I told you, I haven't implemented like ensemble learning myself, but there's so many to choose from. So I'm sure like, I'm sure there are already kind of established practices of like which ones to use together in an ensemble learning situation. But I just don't know about the specifics, unfortunately. All right, so I'll just share the screen quickly.
Yeah, thanks, Justin. I'm going to link that into the class webpage too. It looks like a really good article.
That's a great link. Okay, so I mean, I said like clustering is that kind of the thing. I mean, usually these graphs look like this. So for instance, like here, it could be like, you know, when I talk, you know, just going back to this example about like credit card fraud, like detection, this could be like a certain time and a certain amount, like, and they form a cluster here. And then we look at this data, and then we kind of like make our own deductions there. So this is unsupervised learning for you. Okay. And then there's another one that is called reinforcement learning. This is an interesting one, actually. It uses a reward function instead of what we call cost function in the other examples. We'll talk about it maybe later, but just know that it's a different type of function, or loss function. Maybe you heard about it anyway. But this one in particular uses what's called a reward function. And basically, in this type of function, like every action taken by the algorithm comes with a reward or a punishment. And then the algorithm trains itself to maximize reward. For instance, we have an algorithm, let's say, that is learning to play tennis. The algorithm plays by itself countless times, or plays against an opponent network or model. And there's only one single objective here, that's winning. And but at first it doesn't know how to win. What it does is, like, by playing again and again, and by trial and error, it learns what sequences of moves or actions lead to like beating the opponent. Or another example is, let's say we have a robot that needs to go from point A to point B. And then again, the objective is very clear, just go from point A to point B, but we don't know what's happening in between those points, you know. And the algorithm has to learn how to reach the objective by taking reward or punishment cues from the environment. And I mean, reward can be like, you know, there's a straight kind of, let's say, path. If it goes there, like it's a reward, just can continue going towards A. If there's like a whatever, a hole or something, or some kind of like obstacle, then that's a punishment. So it should like avoid that path, stuff like that. And I'm like simplifying certain things quite a bit, but you know, this is the basic principle. Okay, so I think now it's kind of like a good time to have a look at our neural network example. I came across a video, I think it was a couple of years ago, on YouTube titled "Build a Neural Network in like under 4 minutes" or something, or in 4 minutes. This was a video by Siraj Raval. I think like he's, I'm not sure if he's still one of these like machine learning celebrities, but he used to be one. Like, you know, I used to see this guy like everywhere at some point. And anyway, so it was one of his videos, like a very kind of simple thing. And this was like when back in the day when I was trying to understand what a neural net is. And this video was kind of helpful for me. Basically, it shows you how to build a very simple neural net there. And then the the video kind of like linked a certain kind of like little neural net example. I think the video itself actually showed a 3-layer neural net, but also like in the linked kind of like code, there was a single layer one, which is called a perceptron. So actually I took that one and worked on that a little bit. And the task is actually, the task it is supposed to carry out is very simple, is to take an input with 3 variables, and these variables are only like zeros and ones in this case, and determine what output should come from the data. I'll first show an example in this like semi-original form in Python, and then I'll show you what I did with it in RTC Mix. Like I kind of like translated it to RTC. This was actually a challenge that I wanted to like kind of take. You know, it's like, can we kind of like code neural nets in RTC Mix? Back in the day, like it just, I didn't know it was possible, but it's actually like right now, you can code a neural network in anything. You know, a simple one that is. But yeah.
I code mine in Legos.
you can, I mean, if you can find a way to like iterate it like 1,000,000 times, you can do it. Okay, so let's open that up here. Where is it? All right, so I'll share my screen quickly. Are there any questions, by the way? No, right? All right, now you see, right?
Can you all read that okay? Okay, good.
Should I make it larger, the code?
Yeah, shout it out. I can't see everybody right now, so.
Increase the font size a little bit? I don't know.
Yeah, I can see it well.
I think it's good.
Yeah,
Yeah,
that's fine.
Yeah, it looks fine.
Okay.
Yeah, even I can see it, and I'm old.
So while we're kind of like going over the code, I'll explain more concepts, but I just thought like maybe it would be better to just like also like link it to the code here a little bit. Yeah, okay. So like I told you, this is a single layer perceptron and single layer neural network, which is also called a perceptron. So what we're doing is that, so this is an important part here. So these are our inputs. So we're giving the algorithm these groups of zeros and ones in groups of 3, that is. And for each input, so this is one input, this is another input. So there are 4 inputs here. We're asking it to come up with an output. So actually the task is clear. It's basically we're expecting the algorithm to take the leftmost number in all of these groups. I mean, you can ask the question actually, like, is it necessary, like for this kind of simple task, like, do we have to do this thing? I mean, you can just write some kind of like very simple algorithm that basically just takes the leftmost number out of the list. But that's not the point, you know. Here, we don't even tell what we exactly want from it. We just want to learn by example. So what we give the algorithm is these groups of zeros and ones and the results we're expecting. So from this one, 101, so we want this number. So this is the answer. From here, this is the answer. And then this is the answer, etc. Okay, so there are a couple of things that are important. I'm not sure if I should talk about the activation function. Maybe it's a good time to talk about the activation function. And also let's talk about the, I'll show you in a second. Hold on a second, I'm setting something up here. I just realized that I can use my iPad to draw things. So I'll do that. Okay, so this is, let's say our neuron here. And these are the inputs and output. So we have an activation function here. In this case, it's a sigmoid activation function, which I'll explain in a second. And then for each input, we have weights. So weight 1, weight 2, weight 3. So the weights modify the inputs, and the activation function modifies the output of the neuron. This is actually kind of like the brain of the neuron here, the activation function. Why do we use an activation function, and why do we use a sigmoid activation function in this case? Because it forces the predicted output values to be between 0 and 1. It just basically simplifies, let's say, maybe a complex kind of like data, and just basically just squeezes it between these values. And it creates this nonlinearity here, which is useful for these kinds of purposes. And also, yeah, I mean, it just modifies the input data before passing it to the next layer. And this is our sigmoid function code. And I'll show you what it looks like actually, and it will hopefully make more sense then. Okay, so this is a sigmoid function. I mean, this is a great, it's not the most common activation function these days, but actually it's quite a good one, because it, you see that there are these like almost like flat parts of it. So there, it basically kind of squeezes zeros and ones, or the extreme kind of values, into these sections. And so we don't get so much stuff in the middle. So we want actually these values to be at the extremes as much as possible in this case. Almost like a biological neuron, if you will. There are other activation functions, namely, for instance, like there's this one called ReLU. I think it's much more common these days. And that, let's see if I can find it. It does this kind of like pushing to 0 and 1 thing much better than this actually. But for this purpose, for this example, we're going to use sigmoid function. So this is ReLU, for instance. And it's important that also these activation functions are computationally kind of not very demanding, because we iterate them so many times. Okay, so this is our activation function. And then, like I told you, these are our values. They basically form a 4x3 matrix. And then this is our training set here. And here's a seed value that I use for, okay, so first I should talk about the initial weights. So initially, we don't know actually what type of weights we need in this case. So we have to assign some kind of random weights, and like I know, we need 3 of them in this case. The reason why we generate them randomly is that because apparently optimization suffers when we assign the same value to all weights. So that's why we kind of like generate them randomly. And in this case, I also set like a seed value here, so that like it gives me the same random values each time. It's good for debugging. Skipping the error part for now. And then we iterate. Okay, so we have this, then let's talk about this pre-activation phase. In this part, and this is also called forward propagation, this is an important concept. No learning takes place in this part here. Basically what it does is that it takes a weighted sum of the input, all inputs, and then we also pass it through our nonlinearity, which is a sigmoid function. Let me actually again show you this thing in a different form. Let me see.
While he's looking that up, let me unpack that just a little bit for those that are, you know, just kind of new to this. This weighted sum, it turns out the math of neural networks is really, really simple. All you do is you take each of these weights on those branches coming in, and it's like 0.593 or 0.201 or something like that.
Yeah.
And you multiply it by the number, which is a 0 or a 1, coming through that path. And then by adjusting those weights, that's how you tune the network to respond differentially to different kinds of inputs. That's the magic part.
Yeah, I mean, it kind of looks like this. Let me just show you quickly. So let's say we have, I mean, let me just see the outputs again. So, or inputs. So let's say we have something like this. So what do we have here? 1, 0, oops. Okay, so 1, 0, 1, and then 0, 1, 1. I'll just put the code also somewhere here so you can see that as well. No, sorry. Okay, and then we have 1, 1, 0, and then 0, 1, 0. So this is a matrix. And then we have our weights, weight 1, weight 2, weight 3. We do something like this. So we take the dot product of these weights. And what that means is this. So it's something like, so let me just, where should I write? Just give me a sec. Running out of space here. So 1 plus weight 2. Oh, you don't see it, sorry. Okay. And then weight 3, and then next one, same thing. 1, weight 2, and then 1, weight 3, etc. I mean, we just go down like this, and basically it just gives us one value out of 3 here. So a weight here determines how much a certain input affects that single value we get out of these 3 values here. I don't know if it makes sense. Anyway, going back to the code now.
That's what's fun. I mean, by adjusting those weights, that's how you get it to recognize what particular input you have, because certain inputs will make it have a 1 as an output if the weights are set up, and other inputs will make it have a 0, and that's how you make your classification. That's how you can differentiate between different features in a picture or something like that.
Yeah, exactly. Exactly. But I mean, in this case, like, let's not even go to like more complex calculations. This will be a very simple kind of task here. And basically, like, just understand that, like, it just takes this particular part here, just takes, let's say, this input here, and it just creates just one value out of 3. Taking those weight, like, say, I mean, if it was a regression, they would be coefficients, but here they're called weights. Actually, they're very similar in function. So this is the part where the learning takes place. And this part is called backpropagation also. So we're updating the weights here. And normally this is called a gradient descent, but this is a gradient ascent here because we're actually maximizing the value here, not minimizing it. I mean, I'm not going to go too much into the math here, but just take it for granted for now, and that this is the way you do it here. And we'll come back to it maybe a little later. And then we just basically, so let's kind of like reiterate. This is our input here that we take from like whatever, like initial input, and this becomes our output. And with forward propagation, all we do is we just create this input using weights. And here, it's it updates the weights according to our training set. Okay, so let's run this and see what happens. Okay, so this is actually, let me ask it. So also realize something that I'm only trained this net with 4 kind of permutations of these numbers. And this particular one is not there. but the principle is there. Like I'm expecting the net to kind of understand that actually I'm asking for, let's say, the leftmost number. So let's see what happens. Okay, so this is our final answer here. You don't expect these types of things to give you exactly a 1 or exactly 0. This is good enough. You know, you can deduce that actually the answer is 1 in this case, and you can set your threshold maybe to some other number. You can set, like, you can say everything over 0.85 is good enough for me. It means it's a 1. You can say like anything like under, I don't know, 1.5 or maybe 2 is a 0 for me. I'm sorry, 0.1 or 0.2 is a 0 for me, and you can take that as a number. And in this case, it completely works. The number of iterations will actually make this result a little more accurate. Let's first try with maybe 100 iterations, and let's see the number then. See, it's actually not even like 0.99. It's 98 right now. The more we iterate it in this case, the closer it will come to 1. All right, this is going to take a second now. So yeah, look, it's coming even closer to 1 right now. And it doesn't actually matter whether you use, let's say, an input set that was in the training set as well, because it just, like, it can't necessarily compare, the algorithm cannot compare it to the answers it had. It's more like an accumulated knowledge of some sort. So let's see what happens with this one. So no need to iterate so much. Let's do it 10,000 times. Okay, so 10,000 times gives us this number. I'd say this is even good. At this point, this is good enough for me. I know that it can only be a 0 or 1, so I'll take, I'll consider this a 0. Another one. Okay, let's iterate maybe like 50,000 times this time. Okay, so this is a little higher than others. There may be several reasons for this. But again, maybe if we add another layer to this thing, it could make it more accurate. So we don't know. But again, even this is good enough for us at this point. Okay, so before I switch to RTC mix, let's talk about a couple of important concepts here that don't necessarily apply to this thing, but it may apply to other kind of neural nets, more complex ones. For instance, I told you that I would, like, if I train it more, it would come closer to 1 or 0. That's not always the case with neural networks. Sometimes there's this thing called overfitting. And in some cases, actually, maybe we can even call it overtraining of some sort. I can show you exactly like what I mean with that. Okay, so let's go here. So for instance, here's an example of overfitting. So let's say we have points like this. Something like this, I don't know. Okay, so basically, like, a simple model, or not, doesn't have to be simple, but like maybe like our expected output is something like this. So this is what we expect from our neural net to recognize. Too much training, and especially too much training with small amount of data, can make our network a little too kind of accustomed to the data set. And when you give it something different, it may not look for the right features in that new input data. For instance, like, it can just do something like this instead. Sorry.
Actually, there's a famous example from speech recognition that I'll throw in. It has to do with, you want a speech recognizer to be able to recognize vowel formants, which are kind of like large sort of filter patches. If you overtrain it, what it will do is it will learn the individual harmonics of the particular speaker that they're training it on, and that way, then you can't actually grab the formants because you're too finely tuned. And if it doesn't match those particular harmonics, it goes, I don't know what that is, So you have to be careful about how you do these things.
Yeah, I mean, like this is maybe like a simple example of what it can do, but like it's also when you're training, like, I don't know, it's an image recognition set or something. Model, I'm sorry. Like if you again like train it on like 5 faces, and if you train it like countless times, like I don't know, so many times, then like this model can actually, instead of recognizing or like human face or something, it can just like focus on like little features. I don't know, like maybe a mole or something, or a wound or something on the face, instead of like the face itself. Like these types of things happen. So you want to also like prevent that from, prevent your. You want to somehow like. There's a balance of some sorts. That's what I'm trying to do. Trying to say. So you have to have like the right amount of data, and you should train it like the right amount. But there are ways to kind of like facilitate that. But maybe next week we can talk about that in a little more detail. All right. So another concept. Am I missing something here? So I guess that's more or less it for this one. So let's kind of try to translate this to RTC mix. This is actually, it's, I would say, more of an RTC mix practice. And in particular, like you have to use a lot of custom functions. And that's, I guess, the key thing to take away from this thing. So let's see. So let me show you the patch quickly. Is the patch big enough, or should I make it a little larger? Maybe like this?
Yeah, I like that better personally.
Okay, let's keep it like this then. All right. So there are a couple of things that I want to show here before the kind of net, like neural net itself. I'm not sure if we've done. Brett, did we talk about this open script command here, ghost script command at all?
Just briefly. I mean, we talked about when I was talking about how you initialize variable values for the chaotic equations. And I remember I mentioned that you can have up to 19 of these scripts on an RTC mix object. But yeah, right. you should go through it a little bit.
I mean, Doug Scott also talked about custom functions and how he kind of does this. It's what I'm doing is somehow similar. So okay, let me just show you the score file quickly. So what I did was all of my custom functions are in one kind of script, and I load them first. This actually makes it like easier to do certain things. Like I also separated. First, this is the training part. It's one score, and then there's the and this is where I run the model. It's important because the training part takes longer than others, so there's no need to do it again and again. If I want to just try some new input values, for instance here, already like whatever is kind of done in the training phase, the variables and stuff, they stay there anyway. So I can just like input like new put new inputs here and just try new values. It's just much easier. I'll show you in a second, like maybe like I'll explain a little more. Okay, that's one thing. So should I talk again about custom functions, like how to do them, or is everybody kind of okay with that? Like Doug also talked about it, but if you want, I can again like go over them. Just let me know.
Wait, what do you guys think? You want him to go over a function creation?
What do you mean by custom functions? I don't remember.
Okay, exactly. So there are like if you I mean RTC has many built-in functions, right?
Yeah. Like print.
These things, right. Like for instance, they're all functions. exactly. But you can also create your own functions. Meaning if you do a certain kind of task again and again, over and over again, you don't need to type it out all the time or copy paste it. You can just basically create a function and then just use that little function identifier to run it again. It's
Right, okay.
it just makes it much easier to. I mean, first of all, your score looks cleaner, yeah, I mean, it's just a good practice overall.
Yeah, and we're going to be putting these patches and also the separate scripts if you're running in PD up on the website, so you'll be able to take a look at them. You know, that's probably the best place to start with this, is just try to modify some of these things. You know, especially next week when Onur shows you the actual applications of some of this.
Yeah. But anyway, so I mean, I'll just then very quickly kind of go over it. So okay, so it's a very simple thing after all. This is the structure of a custom function. You have to specify, is this big enough, this text here? Should I make it?
Yeah.
How
Yeah,
do
I
I
think
make
it's
this
okay.
larger? Okay.
Yep.
So the first, this is the type of output your function will give out. So this is, it's very important to know them beforehand. And in this case, my function is called sigmoid function. It just basically creates the sigmoid activation function that I told about. And this one here, it's the input that the function will take. So argument 0, it's a float again. So it's a floating number. And then return, yeah, this is the floating number here. We'll return this. Okay, then we can just basically quickly compare like the Python code and the RTC mix code here. So in this case, actually, I didn't talk about this thing because I'm not sure if there's any need, but anyway, so this particular function here has actually two functions in it. Depending on whether you specify true or false, it gives you either the sigmoid function or its derivative. I didn't use the derivative function here, but I create the separate one for the derivative instead of like putting it in the same one. And then we have the training set inputs, just like here, the same ones. There's one extra here. I was a little lazy not to automate this thing. And at some point in the code, you need to use a transposed version of these input values. And by transposed, I mean, if you look at it, you'll see what it means. So instead of like grouping them in threes, group them in 4. So you take this one, 1, 0, 1, 0. That's one list, one array. And then middle numbers, that's one array. And then the last one. So it's not very, very important, but at some point that's required. So I had to do it like that. But you can totally automate this thing with a loop, which I'll do probably before I upload it. And these are our training outputs, just like here, training set. This was an alternative input that I used, but I'm not using right now. This is how I create my random weights here. Again, if you want to see if you want to set a seed number, just like Python, you can just do it here, srand. So it will just give you the same random numbers each time you run this thing. Great for debugging. That's where I use this function here to create the initial weights. Okay, so this is kind of like an interesting thing. As far as I know, and I'm not sure if maybe that's different right now, but when I wrote this thing, we couldn't actually use, does RTC Mix have matrix mathematical operations right now, or no, right?
No,
it
does not. Right, it does not.
Okay. Okay, so that's why I had to create them from scratch myself. It's trivial. I mean, you can just do it. But this is basically a dot product that's used here. It's already baked in. It's already in Python. Like if you use the NumPy library, it already has a dot product function. But I had to create that from scratch here. And then let me see. So there's this is dot sigmoid. This is a dot product. Later run through a sigmoid function. You can, for some reason, when I separated them, there was a problem. So I just basically combined them in one function. this is for subtracting lists from one another. They have to be the same length, obviously. And there's no like, I didn't like code in any kind of like error messages or something. So probably if you, I'm not sure, maybe like if you use lists of different lengths, you may just crash max MSP. I don't know. Anything can happen.
Yeah, I think it might work, but it'll substitute zeros in for the missing elements.
Yeah.
Yeah, but I'm not sure about that. You're right. It might just crash.
I don't know. I haven't tried it recently with like you know, different values, but it works as is right now. So this is a single. So in Python, if you write something like this, so there's, first take a look at this thing. 1 minus output. This output is a list. So if you subtract it from, if you subtract the output from just a single number, a list from Python, basically just creates a list out of this number, if you will. You know, like, so it's like if the list, if this is a list of like 4 elements, then we get like 4 ones, you know, one after another. RTCMS doesn't do that automatically. So in order to do that, I create like a function called single number list. So basically you give the number and how many times you want it to be repeated in the list, and just gives you that thing. So that kind of thing. And then this is the neural net here, or the learning part, let's say. So this is the forward propagation part. Just like here, I would say this is quite similar. Again, dot sigmoid function. It just basically takes, again, dot product and just runs it through the sigmoid function. This whole thing here, it looks a little more kind of convoluted, but actually this whole thing, I wrote it in like different lines because it just looks cleaner. And I might have run into like some kind of problem when I basically put everything inside one another, like in parentheses and stuff. But in any case, it's just the same thing, but written out in like on separate lines. And at the end, where are we? Yeah, just like here, you know, I update the weights. It's actually clearer. So in this last step, I update the weights according to the predicted values that I'm getting like each iteration. And this is the training phase. And then this is the kind of like the main, let's say, prediction phase. You run the model here. Okay, I already talked about the dot product. What we have here is this one. The print is always separate, but this basically equals this one. The sin 0 here, I could have called it weights. I'm sorry about like the variable names. They're a little kind of all over the place. I'll probably standardize them a little bit in the end. But so this runs it. So let's try this thing. Let me just check the values quickly. Just check this thing. Now I'm going to run this thing 100 times again. And the value I'm going to look for, ask for is 100. So let's start this thing. Oops. So Go script just loads the functions like I told you. And these are my initial weights here. So let's train this thing right now. It was very quick. It's only 100 times. These are the weights. So let's try the value here, see what happens. Okay, this is pretty close, but I can train it again and again here, for instance. So train again, another 100 times, another 100 times, another 100 times, etc. So let's check the value again. See, now it's closer. Compare these two. Same thing happens.
Magic. It's learning.
It's learning, yeah. Okay, so let's ask our network, our model another, like I say. Okay, so this is not great. I mean, it's still like closer to 0, but let's train it, what do I know, like 5,000 times this time. It's gonna take a while. It's a little slower. Okay, okay, this was not too bad. Well, I mean, still not there. 10,000 times this time, maybe. I mean, we're getting there. You get the ideas. It doesn't have to be like at different values, different inputs can perform like differently in this case. So you may need to train it more if you want like every single input to give you like a good prediction. But actually, in real life, this is a good prediction. You know that it's closer to 0. So.
Yeah, I have a stupid example I'll link in from a class that's like, 5 or 6 years ago. And basically I said, if it's less than 0.5, it's 0. If it's greater than 0.5, it's 1, which is
exactly.
ideal.
I mean,
but yeah.
I mean, in a binary system like this, it will completely work. But, if you're obsessive, if you want your model to be the best in the world, then you train a little more. Again, I mean, this is maybe a stupid example in the sense that, it's a very simple task. You can just do this thing algorithmically in a single line. But that's not the point, like I told you. The point is that this model didn't know what we asked for. It just figured it out by itself. So that's the fascinating thing about it. And it adjusts the weights also by itself. So this is the kind of like, this is the magic of machine learning, I would say. And also I have to like say something, this is a good practice, and I recommend everybody to kind of like build a neural network like this from scratch, maybe even like a 3-layer network or something if you're into it. But the reality is that you will never use the neural network you created yourself in real life. You will always use a library. They're faster. You can do more things with that. Like they're overall like much more user-friendly, but it's good to know how they work. There are a lot of people who just use these libraries, but they just don't know what exactly is happening. Like, this whole black box thing happens in that case because, the certain person like, doesn't care. It's not a huge deal, but I recommend everybody to kind of like go over these things. It will kind of demystify certain things for you, and you'll understand even those libraries better.
Yeah, I think, a lot of this, we're just kind of throwing different concepts and different ideas out there that you can choose to engage with or not. I mean, there may be something that you find particularly fascinating about this, and maybe you've got an idea of what you want to do. In that case, Onur in particular can sit down and help you kind of understand some of the stuff, and especially after next week when we show you how you can actually use these libraries and just like take something that's given and, start running classifications on it and things like that. That's when it gets kind of fun. Yeah, if you're kind of freaked out by this particular set of coding, don't worry about it. Yeah, I mean, we still have got a lot of ground to cover. We're going to go from here, and we're going to be talking about setting up an internet radio station, all kinds of stuff like that. So hang tight, and yeah, it'll be fun.
I mean, I can show you also a couple of like little things that are not necessarily like about music or art or sound, but because this class is also like, we're one of the themes is like web audio or something. So I'm actually, next week I'll try building something using, there are a lot of these like web tools that, that you can use to create like machine learning kind of models inside your browser, and there are also ones that are geared more towards artists and stuff. So I'll see if I can do with them. Another plan that I have is that because next turn is going to be Unity, right? Like you're going to use UX. So maybe we'll see how we're going to do with time. But one of my plans is also to kind of show you this machine learning kind of library that functions within Unity. It's quite nice, and it may give you also an early taste of Unity as well. But anyway, so.
Yeah, Joshua just posted
really
a good link. Yeah, Joshua just posted a good link for people that are looking at things too. Thanks, Joshua. I'll put that in the on the web page. Yeah. Sorry, Onur, go ahead.
Okay. I mean, it's crazy. For this one, it's MNIST is kind of like it's a data set, very like popular one for number recognition, and this completely runs in the browser. It's a deep, neural network. And like within basically a minute or something, it's still training. It's training, and at the same time, like it's we can see like how it's performing here. So these are like handwritten digits here, and see how the accuracy goes up slowly, just from a couple of minutes of training, basically. And this is like the point is that this is possible within your browser as well. This is not running from a server; it's just running in the browser. let me see. And first, it's using as an activation function. It's using ReLU here. We can see that. Anyway, so that's one thing. Maybe as a last thing, I want to show you also, if anybody's interested, this is not necessarily about machine learning, but it's this editor. I don't know if any of you are using, do you guys know about Atom editor at all? So anyway, it's a kind of like a popular one. And the nice thing about it is that you can actually write like plugins for it, or like, it also has a lot of these packages that you can install on it. I use this for basically kind of, so I use it for Python as well, but I like it especially for RTC mix. If you could compile the RTC mix binary, this is quite nice because you can run with certain packages RTC mix audio within Atom. I'm not sure if you're gonna hear this thing. I guess I have to restart the sharing, right? If I want to share the audio.
Yeah.
Okay, let me do that quickly. Okay. Oh, I need to change this thing to 48K, right? This one.
Boy, I'm noticing the delay on my window when I do a gesture, and then I see it on yours. It's quite something.
Oh wait, I'm not sharing the right screen then?
I'm seeing your desktop. I'm also
Oh.
seeing, yeah, like everybody else.
Oh, sorry.
That's okay. It's kind of fun.
Share screen. Desktop 2. Okay, now you see it, right?
Yeah, that's it. That's it.
Okay, great. All right, so yeah, this is the one thing that Brad told me to do. Like, you just had to set the set this to 48K.
For Zoom.
Oh god. Did we have this problem before? We had it, right? I remember like.
Yeah, you had to reload the file, I think.
Okay, let's give it another try. What if I just played like this? Let me see what happens. Nope. Okay, so 48 is needed indeed. I mean, this is a random example. Like it's from one of these example scores. But the point is that you can just run the code within Atom. It has a nice code highlighting thing. Basically, RTC Mix more or less uses the C score highlighting file. If you can set it, just highlights it nicely. But that's not the best thing about it. So we're at this point, like we're working on some kind of auto completion for RTC Mix. I find it very, very kind of useful because I don't have to look at the reference website all the time. So for instance, if I just write this wave table right there, so I can just write anything. Like it also jumps from, let's say, like by using tab, you can just jump to different values. We're gonna add all of the instruments here to the autocomplete. This could be like a RTC Mix development environment, actually.
So that was playing through through Atom somehow, not just like you can just open a terminal in Atom and run
Well,
RTC.
no, there's a package called, let me see, where is it? Process palette here. You can add comments to it, like terminal comments. So what I did was, let me find the RTC mix core. So it just basically does this. It takes the file's path, absolute path, and runs it through the RTC mix binary here. And I assigned a keystroke to it as well. So it's very, very quick. It's great.
Let me interject something here. You probably noticed that that example sounded in mono. It turns out there's a problem with Zoom. If you have above 5.1, we can't get it to run in stereo. Doug Scott became so incensed by this that he's had Apple contact Zoom and yeah, just say, what's the story here? Because you promised good audio in your upgrade. So if you're upgrading Zoom to something greater than 5.1, at this point, we're not quite sure how to get stereo to happen on it. I'm sticking with the old Zoom for now.
Yeah, unfortunately, I upgraded at some point without even thinking about it, and now I'm suffering because of that. But anyway, I mean, for today at least, like I didn't need stereo audio or anything like that, so that's fine. But hopefully, we're going to find a solution to that.
And if any of you have any idea about how to do stereo in the upgraded Zoom, let us know, because we can't figure it out. Okay, so I think that's all I have. Are there any questions? I mean, I know this today was a bit like maybe like too abstract because it's just a bunch of code and like some weird thing that gives you 1 or a 0. But it's actually the principle that counts, I think. But anyway, if there are any questions, anything, you know, about whatever machine learning uses, if this was the first time you heard about neural networks, anything, you know.
I'm wondering if you could say a little bit more about, I don't know, I've been playing around with like machine learning applications in Max. So with like common stuff that I could find. For example, like the stuff that comes from Mubu, or with Mubu, from IRCAM or ML Star, ML, these sorts of things. But I thought that it goes up to a certain point, but it doesn't ever get really complex. It doesn't go further than pattern recognition on some level, at least with you know, with like this motion recognition, or then you can have vowel recognition, these sorts of things. And and on the other hand, of course, you can do the whole like analysis thing with Mubo and so forth. But I always wondered if there is smart ways to maybe implement code or just different algorithms into Max to like take it to a different step. Or maybe I just didn't understand the real potential of this.
I mean, by their very nature, those tools are limited to a degree, but actually at the same time, they make it very easy to prototype like certain ideas using like, I mean, otherwise, like maybe you would need to like use a library like a like TensorFlow or Flow or like PyTorch, like within Python, like to create like certain things yourself. And it also like introduced some kind of limitation, obviously. I haven't tried Mubu myself. ML Star, I think I tried a little bit, but to be honest, I haven't used these libraries within Max and MSP like too much. But I actually recommend you to take just like a machine learning introductory course. That's not necessarily about like audio or anything, just like get the basics like that. And then you can basically just like use these much more developed tools like TensorFlow or whatever to implement whatever you want to do. It will give you much more flexibility overall. Not like tools designed for like music or audio, but like general purpose tools. That's what I can recommend.
Is there a specific course you can recommend? So
many of them, but recently, actually, Alessandro also I talked about it, I think a while ago, maybe like she told me only, I forgot, but there's a Cadenza course. Let me just try to find the link. I think I have the link somewhere here.
That's the one that Rebecca Fiebrink did, right?
Exactly,
Yeah, it's a
exactly.
very
She's
good
doing it
course.
right now.
Yeah.
Actually, it just started. It just started, I think, or the new kind of like iteration of it just started. And she teaches this tool called Wakinator, if I remember correctly.
Yeah, we're going to show that next
could be
time too. Yeah.
Yeah. So I'll try to, depending on the time, that's also one of my plans. But yeah, I mean, I can show you that as well. But that course, let me just find it actually while we're talking about it. It's, or if anybody can just find it before I do, you can post it. But I think it's here somewhere. Online courses. This, sorry. This is it. I'm just posting in
This here?
chat.
Oh yeah, yeah. Okay.
I haven't done this one, but I just signed up for it. I will be doing it. I did more general purpose ones and a very like easy one on the Coursera. I believe it was called. Anyway, I mean, I'll find all these links and like post them later on. But there's so many of them, just countless like courses,
I see, but then as far as I understood it, I can implement then TensorFlow into Max as a JavaScript. Is that correct?
Well, I mean, TensorFlow has a JavaScript like kind of version. I'm not sure how it will perform within Max. Is there a Python object in Max right now that works?
No.
I mean, what you can do is
Nicola's right though. There is a JavaScript object, and that should potentially work, I think.
Yeah.
Yeah.
Yeah, at least that is sort of the option that I've seen around that people would be using. That also, for example, the people from Google Magenta are using in order to get TensorFlow into Max, and Max for Life is as a JavaScript.
Okay, yeah, if it works, great. Use it by all means.
I think.
Go
ahead on.
No, I mean, it's just if it works. I mean, I've used like JavaScript inside Max, but I remember having some limitations there with something. Maybe I'm wrong.
Yeah.
But then again, like you don't have to connect. Like you can also like just send like OSC data or something to Max. It doesn't have to like. You can just run elsewhere. It depends on what you want to do.
Yeah, it's also, I think, part of the problem, at least for me conceptually, is trying to figure out how to define a problem that could be solved using machine learning for my musical goals. A lot of that has to do with, say, interactive real-time work, because the machine learning operations hold the promise of being able to recognize things that it can hear. And if you can create an algorithm that's going to respond to those things, then all of a sudden it opens up a real interesting world that, where you can define your interaction based on the sound of things that the computer is receiving. But again, that's pretty tricky, and that's a lot of data to deal with too. But they're getting better at this. I mean, speech recognition, that's pretty remarkable, and that's real-time sound basically. So yeah, I think there's a lot of promise here, but I don't think it's been met yet.
I thought that Mubo library has quite some good resources for that.
Yeah, again, I'm pleading ignorance here because I haven't done anything. Yeah.
Yeah. I mean, that was the best ones that I found so far in Max for this sort of goal, which I've also been trying to find out how
again,
to
like with machine learning, one thing I'm noticing is that like it's important to have a very clear kind of like goal. Like sometimes actually they're better, most of the time actually, like there are better ways of achieving what you want to do without using machine learning. So it's depends on what you want to do actually, like what you're trying to do. Maybe like what you're looking for is like a simpler algorithm, a couple of if then else statements in some ways. But I mean, we can talk about it if you want, like we can like meet on Zoom if you want to discuss something, a project or something, and try to find like a way to implement. So
Oh yeah, yeah, that would be great.
Cool.
Justin just posted something here. Large data sets. Oh yeah, these are great. These types of things.
Yeah, David sent some
Especially
good links
if you're
too.
working. Oh yeah.
Yeah, I'll collect all of these and I'll put them
This
on
one,
the webpage.
I know this one.
Yeah, I'll collect all these, put them on the webpage, probably tomorrow sometime.
Yeah. Yeah, data sets are very important, like especially if you're working with like deep learning kind of models. It's like there's no way, let's say, this a normal like single person can collect like all that data. So you just basically, a lot of people for many purposes they use these like large data sets. Let's say even if you are, for instance, for image recognition, you know, like you're just trying to build something that distinguishes between like different types of clouds, let's say, you know, or a cat and a dog. You still need a trained. You can't just like train your algorithm usually with like cats and dogs. You have to train it with like something else, and like kind of like it's and I'm trying to find like a simpler way of explaining it, but it needs to have some kind of pre-training, you know. And for those things, you usually use these data sets that are found online. It's good to have like
this is Dan Ellis's group at Google.
Which one is that? Oh, the audio set. Okay.
Yeah, yeah. If you go to About Us, he's right there in the middle.
Oh yeah. Okay. Great. Yeah.
Okay, gang.
Cool.
Well, I think we'll call this. We'll call it a wrap. I'm going to turn off the recording now. So again, next time, Onur is going to be showing some real live applications of this stuff. And if you're interested, you know, drop us a note. Like I said, I'll try and get all these links up online, you know, as a resource for the future and whatnot. And yeah, so yeah, Onur will be next week, and then the following week is Lara Lewinson will be showing some of her recent work, which is pretty amazing. So yeah, and then there's the election and the class afterwards, which may be good or may be bad. We'll see. Okay, so I'm stopping my recording now.